Okay, so I'm going to talk about a document which is a consensus on validation of forensic comparison systems in the context of casework. For those of you who don't know me, let me just adjust the camera maybe a little. So for those of you that don't know me, I am director of the Forensic Data Science Laboratory at Aston University. We are doing research, we have ongoing research projects in forensic voice comparison and fired cartridge cases. We've done some work on forensic anthropology. We're doing some work on communication of likelihood ratios, where we've started some work on cell site analysis, and in the future, depending on if we get funding, we're hoping to do some work on fingerprints. I have for a long time been working on issues related to calibration and validation. Excuse me, I'm just going to change my audio settings if I can find this setting. Okay, I'm going to mute. So I'm also a practitioner, and I've been involved in casework in multiple different jurisdictions around the world. And I am also chair of the Forensic Science Committee of the British Standards Institution, and we contribute to developing standards for ISO. Some of my past experience includes being a scientific counsel for the Office of Legal Affairs at Interpol. So thanks to the funding agency that supported this research, and thank you also to everybody who contributed to the development of the consensus and to the development of this particular presentation. So all the opinions are expressed on my own, unless explicitly stated otherwise. Obviously, if I'm quoting from the consensus, there are a bunch of other people who agree with me. The publication is available. It's open source. You can find it at this location. It has 13 authors and an additional 7 supporters. The supporters were generally people who were originally invited to take part, but for one reason or another were not able to attend the original meeting. But after the end of the development, were given the opportunity to add their support to the document. So the contents of this presentation, we're going to begin by talking about the scope, then move on to talking about the methodology that was used for development of the consensus. We'll talk about the actual document that was produced, summarize the key points from that document, and then talk about some issues that are necessary to understand the consensus. And so those will be calibration, the log likelihood ratio cost, abbreviated to CLR, that is our metric of performance, and Tibber plots, which are a graphic representing the performance. And finally, I will give some reflections on broader issues related to validation and standards and guidelines. So to begin with the scope. So the scope for the consensus was validation for the purpose of demonstrating whether, in the context of specific cases, forensic comparison systems are or are not good enough for their output to be used in court. So this is about, not about validation in general, but this is actually about, I've got a case, is my system good enough to be used in this case? So for use in specific cases. The consensus as written states that the scope is forensic voice comparison systems. But if you make a few wording changes, a few minor wording changes, then the statement of consensus is applicable across multiple different branches of forensic science. I would suggest any branch of forensic science which involves comparing things. So the scope addresses scientific matters that could have a bearing on legal decisions, but is not directly addressing legal matters. The scope also was, as originally limited, was originally written, was limited to systems that are based on relevant data, quantitative measurements, and statistical models, and that output numeric likelihood ratios. Again, I would suggest that it actually has broader applicability, and it's also applicable to systems based on human perception and subjective judgment, and I will talk more about that later. To move on to the methodology, how was the consensus developed? So we had invited participants who the idea was when we brought these participants together, they could reasonably consider to be representative of the relevant scientific community. They included individuals who had knowledge and experience of validating forensic voice comparison systems in both research and in casework contexts. And they included individuals who'd actually presented validation results to courts. And it was not just limited to people who work, it was not just limited, for example, to practitioners of forensic voice comparison. We also brought in individuals who could bring a legal perspective, and individuals had knowledge and experience of validation in forensic science more broadly. I'll not go through all the details, but our methodology involved first having a 2-day meeting back in the days when we could have physical meetings. And at those meetings, people discussed their ideas. Everybody got the opportunity to speak. In fact, we started with everybody giving a kind of short presentation. Everybody got to speak individually, and then we took off and had the discussion from there. And the idea was initially the moderation was supposed to be a light touch moderation, which has kept us into scope, but gave people the opportunity to share their ideas. Notes were made. And by the end of, it didn't take a whole 2 days, we'd reached a consensus. That was followed by a series of online meetings. And the final set of online meetings followed a formal process that, as is used for ISO for standards development, where people had to submit comments, they had to submit concrete proposals for changes, and then at the meetings we decided to accept or reject particular proposals. And so the whole process took almost a year. So that produced a document as the output stating the consensus. The document contained the statement of consensus itself. To keep that statement of consensus succinct, we had informational appendices. So background information was provided in appendices. And the statement of consensus itself contains recommendations. So it's a guideline. This was not developed through the auspices of a standards development organization. This was an independent effort. So it's a guideline, it states recommendations. Any sentence which has the word should in it states a recommendation. The statement of consensus itself, excuse me. Statement of consensus itself begins with the scope, moves on to calculating a likelihood ratio. It's necessary to say something about the background of what it is we're doing so that we can decide whether it's calibrated, whether it's validated. So it talks about the propositions, the relevant population, the conditions for the forensic evaluation. It talks about calculating a likelihood ratio. Also the important step of calibration. Then it moves on to talking about the actual validation processes and procedures, the validation data, and decisions about whether the calibration and validation data are sufficient. It then continues on to talk about anticipatory and case-by-case validation. So the distinction being anticipatory validation is you conduct a validation study under a particular set of conditions. Then when the cases come in, you say, does this case have conditions sufficiently similar to an existing validation study? And if so, I can use that validation study for this case. If the case comes in and you don't have an existing validation study that's sufficiently similar to the conditions of the case, then if you want to proceed, you'll need to do a case-by-case validation, and you'll have to do validation for the conditions of that particular case. We then had recommendations about presenting the validation results, followed by a section which was more informational about the relationship between conditions and performance of systems. So there's an interaction. The validation results will depend on both the conditions of the items that are being compared and the performance of the system. All systems will perform more poorly when the conditions of the items that are being compared are poorer. And it could be that one system may work better under a particular set of conditions, another system may work better under a different set of conditions. It then talks about the validation threshold for CLR. CLR was our metric for performance. And finally, it talks about making recommendations about a decision as to whether the likelihood ratio that results from the actual comparison of the question source and non-source items, is that likelihood ratio value supported by the validation results. At the end, there's a summary of the key points from the statement of consensus. So let's move on to those key points. In the statement of consensus, each paragraph is numbered for reference purposes. And in fact, in my casework, we've developed a checklist that is referenced to the paragraph numbers. And that's so that we make sure that we're actually following these guidelines. And then we can have a second practitioner check the report and check whether we have followed the guidelines or not. So it begins by saying the forensic practitioner should communicate to the court what propositions the forensic practitioner has adopted for the case, including what they've adopted as the relevant population. So this is important so that the court understands what question it is that the practitioner is addressing. And that's necessary so the court can decide whether that's an appropriate question, and also so that they can then understand the answer to that question. But it's also necessary to have a prior understanding for what is being validated. And along the same lines, the forensic practitioner should communicate to the court what the conditions are of the question source and the non-source items. Something which I think is very important is the forensic comparison system should be well calibrated. This is something which should be done as part of the evaluation prior to doing validation. I'm going to talk a lot more about that later. The validation data should be representative of the relevant population and reflective of the conditions for the case. So if not, then the system is being validated under conditions which are different from those of the case. And the results then will not necessarily be informative as to how well the system will perform under the conditions of the case. It should go without saying that the system that's being validated should be the system that is actually being used in the case as well. It should go without saying, but I have been involved in cases in which one system was validated and a different system was presented to the court. So one has to make a decision about whether the data are sufficiently representative of the relevant population and sufficiently reflective of the conditions for the case. That decision ultimately is a subjective judgment. So that comes down to the subjective judgment made by the practitioner, right? So there's a question earlier about are systems based on relevant data, quantitative measurement, statistical models. Are there human factors issues? Yes, there are human factors issues because you have to decide issues like what data am I going to put into the system? And ultimately, that becomes a subjective judgment. If your procedure is relevant data, quantitative measurement, statistical models, you are making this subjective judgment at the very beginning of the process before you have looked at and analyzed the properties of the known source and question source items. And then after you've made that decision, the whole of the rest of the system is automated so that this is much more resistant to cognitive bias than a procedure in which, for example, the ultimate conclusion as to the strength of evidence was based on a subjective judgment. But this decision is a subjective judgment and therefore is something which could be disputed. And for transparency, it should be made clear that this is a subjective judgment and this is what was done. It can then be disputed before the court, and the court can, at the end of the day, make a decision. The court can decide, first of all, was the question that was being answered an appropriate question? And then were the data that were being used data that would actually answer that question? And were the data that were being used for validation representative of the case conditions so that they would be meaningful, they would give meaningful representation of the performance of the system under the conditions of the case. So the validation results should be presented as a tipper plot. That's our graphical representation of performance, and as a CLR value as our metric of performance. Once we've got a metric performance, we can then think about what is the validation threshold. And so the consensus was that the validation threshold should be a CLR of 1. The reason for that we'll get into more depth later. But as long as the CLR value is less than 1, then the system is producing useful information. Then, to decide whether the likelihood ratio value calculated for the actual comparison of the known and question source items, to decide whether that is supported by the validation results, that value should be compared with the values shown in the table plot. And we'll explain more about that later. Okay, so what progress are we making? I think we're making good progress. We've talked about the scope, we've talked about methodology, we've talked about the document that was produced, and we've gone through the key points. And now I'm going to talk about calibration, log likelihood ratio cost, and tipper plots, which fills in some necessary background information in order to understand some of the things that are stated in the statement of consensus. So first, calibration. What is a well-calibrated likelihood ratio system? Well, here it is. It may look like a little bit of an enigma or a piece of poetry. A well-calibrated system is a system for which the likelihood ratio of the likelihood ratio is the likelihood ratio. What does that mean? What it means is the system is outputting a likelihood ratio value. So let's take our likelihood ratio value here. If I can wake up my mouse, there we go. There's a likelihood ratio value there. And that's a value output by the system. And so we're asking, here's a probability density function. Probability density function for same source. So what's the probability function value for that likelihood ratio value if it came from the same source? Divided by what's the probability density function for that likelihood ratio value if it came from a different source, right? So we're putting in pairs that are either same source pairs or different source pairs. So, and our system spits out a likelihood ratio value for a particular pair. And then we can say, well, what's the probability density value for that particular likelihood ratio value if it had come from the same source comparison versus if it had that particular, what's the likelihood ratio density for that? Sorry, what's the probability density for that likelihood ratio value had it came from the distribution of different source pairs? And if the answer to that is the same as the likelihood ratio value that you originally got out, then that's a perfectly calibrated system. The likelihood ratio value The likelihood ratio of the likelihood ratio is the likelihood ratio. Let's look at that graphically. Here are some graphical representations of perfectly calibrated systems. On the x-axis, we have calibrated log likelihood ratios. These are natural logs. And these perfectly calibrated systems have Gaussian distributions. And the two Gaussian distributions have the same variance. So one is a different source distribution that comes from different source pairs, and the other is a same source distribution. And if we set it up like that, then the perfectly calibrated systems have the means of the different source and same source pairs are separated by one variance unit. They're one variance unit apart, and they're symmetrically placed around a log likelihood ratio value of 0, which corresponds to a likelihood ratio of 1. So the top example here, the sigma is 1. So sigma squared, the variance, is also 1. So the mean for the different source distribution will be at -0.5. And the mean for the same source distribution will be at +0.5. They're one variance unit apart. If we go to the second panel, the standard deviation is 2. So the variance, sigma squared, will be 4, which means that the mean for the different source distribution will be -2, and the mean for the same source distribution will be a +2, i.e. they are 4 variance units apart, and they are symmetrically arranged around a log likelihood ratio value of 0. And we follow on for the other example panels. If our sigma is 3, then sigma squared is 9. Therefore, the two means are at -4.5 and +4.5. If sigma is 4, then sigma squared is 16. So the two means are at -8 and +8. So all of these systems are perfectly calibrated systems, but they don't all have the same performance. So the systems toward the bottom have better performance than the systems toward the top. And you can see that the distributions for the same source and different source comparisons are great. They have greater separation. As you go toward the bottom, those are better performing systems. So those are some examples of perfectly calibrated systems. How do we calibrate a system? Here's an example of some results that are not calibrated. These are uncalibrated log likelihood ratios that I'm representing. And some important piece of vocabulary, I'm going to use the word score. When I use the word score, I mean an uncalibrated log likelihood ratio. When I use the word score, I do not mean a similarity score. Okay, so score means uncalibrated log likelihood ratio. So here's the distributions of different source uncalibrated log likelihood ratios and same source uncalibrated log likelihood ratios. You can see that these are shifted toward the right, and it will also turn out when we examine it that these two distributions are too close together. A step toward how we would calibrate this, well, remember I said before, for a perfectly calibrated system, the likelihood ratio of the likelihood ratio is the likelihood ratio. Well, let's calculate, these are distributions of log likelihood ratios. Let's calculate the likelihood ratios of these likelihood ratios. So we'll go along the bottom here, we'll take little steps along the bottom, and each step we will say how many times higher is the same source curve, the blue curve, than the different source curve, the red curve. So how many times higher is this probability density function than that probability density function? That gives us a likelihood ratio. And then what we'll do is we'll take the log of that likelihood ratio. And if we do that, this is the answer we get. So this we can create by taking these little steps along. At each point along the x-axis, we say how many times higher is the blue curve than the red curve. That gives us a likelihood ratio. We then take the log, the natural log of that likelihood ratio. And the result is a straight line. And then that straight line gives us a mapping between our uncalibrated log likelihood ratios, or scores, and our calibrated log likelihood ratios. So for example, if we looked at a score value of 4, we could then go up here and we could read off on the left. That would correspond to a calibrated log likelihood ratio of -2. If we had an uncalibrated log likelihood ratio of 6, we can go up here and then read off the value on the left. That's about 4. So score of 6 corresponds to a calibrated log likelihood ratio of 4. So let's take all of these data. We will put them through this calibration function. And the result we get is this. This may look familiar. We saw it a couple of slides ago. This is a system in which the different source and same source distributions have means at -4.5 and +4.5, and their variance is 9, or their standard deviation is 3. And in fact, I could have told you this would be what the perfectly calibrated system would be from the very beginning, because if we go back, if we look at these distributions, different source mean was 3, same source mean was 6. The standard deviation was 1. So sigma was 1, sigma squared would also be 1, so that these same source and different source means are 3 standard deviation units apart. And once I know that, then I know what the perfectly calibrated version would be. It would be this. Can I demonstrate that this is now perfectly calibrated? Yes, I can. Imagine that you did the same process as we did before. We take little steps along, and at each step, we say how many times higher is the blue curve than the red curve. And that gives us a likelihood ratio. And then we'll take the log of that likelihood ratio. And when we do that, this is the answer we get. So we now have a straight line, which is mapping from log likelihood ratios to log likelihood ratios. And that straight line is this diagonal in which the intercept for this line is at 0, and the slope of the line is equal to 1. And this is the identity mapping. So for example, let's, if we ask if we go to the log likelihood ratio is 4, and we say, well, what would that correspond to? We can go 4, we can go up to here, we can go over to the left, and the answer is 4. So this is an identity mapping. This is already a calibrated log likelihood ratio, and if we try to map it, if we try to recalibrate it, it maps to the same value. So that was a method by which we could do calibration. We can do this mathematically. The formula for a straight line is y equals a plus bx. So we need to calculate what is the value a, the intercept, what is the value b for the slope. We can do that using these Gaussians with the same variance. However, in practice, we tend to use logistic regression because it is more robust to violations of assumptions about it being a Gaussian distribution with the same variance. It doesn't depend on those assumptions. So we use logistic regression to calculate a and b, the intercept and the slope. So how do we apply this? Well, first of all, let's have our initial model, which may be a very complicated model. We may be in a very high dimensional feature space and have a very complicated model. And the value we get out of that, we don't think is going to be a well-calibrated value. So we are going to treat it as a score. We are going to treat it as an uncalibrated log likelihood ratio value. We can put our question source feature vectors in, our non-source feature vectors in. We've trained the model using feature vectors from the relevant population. We get out a score. We take that score and we then input that into a calibration model. We put that into a calibration model. It's a very simple model, straight line, y equals a plus bx. And we then use that simple model to get out our calibrated log likelihood ratio. And it produces calibration because it's a very simple model and you now have a very large amount of data for training those two parameter values. Whereas in the earlier model, it was very complicated. You had lots of parameter values you need to estimate. So the calibration model at the bottom, that needs to be trained. How do we train that? We need some same origin scores and we need some different origin scores. How do we generate those? Well, we go up to here to our initial model and we are going to put in pairs of items. And we're going to put in pairs where some pairs we know are same source pairs. So we put on a whole bunch of same source pairs, and for each of those, we get out a score, and then calibrated log likelihood ratio. And we also put in a whole bunch of pairs in which we know that these are different source pairs. Each member of the pair comes from a different source. And we get out of that a whole bunch of different source scores. And then we can use that collection of same source scores and that collection of different source scores to train our calibration model. Importantly, the scores that we use for training the calibration model should be representative of the relevant population for the case and should reflect the conditions of the case. And that includes if there's a difference in the conditions between the question source item and the non-source item, that mismatch should be represented in the pairs that we put in, that we use for training the calibration model. So that's how calibration works. We can apply that to a system that's based on relevant data, quantitative measurements, and statistical models. We can also apply that to a system that is based on human perception and subjective judgment. We apply exactly the same procedures. We need to train the calibration model. So in order to train the calibration model, we need to give the human practitioner a set of pairs where we give them a set of same source pairs. We give them a set of different source pairs, and for each of those, we get out a score. We're going to ask the practitioner to try and give us a likelihood ratio, but we're then going to treat that as an uncalibrated likelihood ratio. And we use the results from the pairs that we put in there. We know are same source pairs, and the results that we know are different source pairs to train the calibration model. And then finally, we ask the practitioner to look at the actual question source and non-source items, give out their likelihood ratio, their uncalibrated likelihood ratio, and then we can put that into our calibration model and get out a calibrated log likelihood ratio. So this calibration procedure can be applied to both procedures based on relevant data, quantitative measurements, and statistical models, and procedures based on human perception and human judgment. So you need data to train the calibration model. Here's the good news. Calibration data are free. Why are they free? They're free because if you are doing validation, you can do cross-validation. So you can train the calibration model by doing cross-validation using the same data as you are using for validation. You should absolutely do validation and you should absolutely do calibration. But if you're doing one, you already have the data that will allow you to do the other. So that's the good news. If you're interested in finding out more about calibration, there are some references in the consensus document itself. One of them that I'd like to point out is a paper I wrote quite a long time ago now, but it's a tutorial on logistic regression, calibration, and fusion. So it's intended to be introductory level. And some of the pictures I just showed you actually came from a paper that was published just this year, this one in the middle. And you may also be interested in looking at the videos that were recorded from the presentations that were given at a symposium on calibration that occurred earlier this year. So the reference there is at the bottom. Let's move on to talking about the log likelihood ratio cost, which is going to be a metric of performance. We're going to put in same source pairs and different source pairs where we know what the truth is. As I said before, these need to reflect the relevant population and the conditions of the case. We put these into the system, and then we get a likelihood ratio value out. And for our validation data, we know the answers. We know whether it's same or different. And we get the actual answer that our system provides us with. Let's think about same source pairs. If we know we've got a same source pair, a good answer would be very large likelihood ratio. A less good answer would be a small likelihood ratio value that's greater than 1. A bad answer would be a likelihood ratio less than 1. And a very bad answer would be a likelihood ratio that's much less than 1, if we know that it's a same source pair. So that's what's represented here by this same source function. The same source function is assigning a penalty value. For example, let's say we know it's a same source comparison and we get a likelihood ratio of 1,000, which corresponds to a log 10 likelihood ratio of 3. And the penalty value there is really close to 0. In fact, in this diagram, it looks to be at 0. It's not quite at 0, but it's close to 0. If the performance isn't quite so good, let's say we got a likelihood ratio of 10, i.e. a log 10 likelihood ratio of 1. Well, we can see there the penalty value might be something like 0.1. That's not as good a result, so the penalty value is higher. If our likelihood ratio was 1, then we would get a penalty value of 1. That's not as good a result. We know it's the same source comparison. We'd like a large likelihood ratio. And then if our likelihood ratio is less than 1, so our log likelihood ratio becomes negative, then we get a higher penalty value. For example, if our likelihood ratio is 1 over 1,000, our penalty value would be 10. So what we do is for all of our same source comparisons that we put in, we get out the penalty values. We then take the average, the mean penalty of all of those penalty values. We do the same for the different source pairs for which a very small likelihood ratio, a very large negative log likelihood ratio is a good result. We use this other curve. We put all of our different source pairs in. We get the likelihood ratios out. We calculate the penalty values. We take the average of those. And then we've got two means. Mean for same source, mean for different source, then we take the mean of those two means. And that's how we calculate CLLR as our metric of performance. Here's the mathematical formula for doing that. I'll say no more. We want to understand what does it mean. The better the performance of the system, the smaller the CLLR value will be. Smaller is better. This is like classification error. The smaller the values, the better. So a system that always responds with a likelihood ratio of 1, irrespective of what the input is, provides no useful information. Right? So whatever your prior odds are, the likelihood ratio is always 1. You multiply your prior odds by 1. Your posterior odds are therefore the same as your prior odds. You haven't made any change in your beliefs. You got no useful information. If you have a system like that, that's providing no useful information, it will have a CLLR value of 1. We can check that by going back here, and CLLR value, a likelihood ratio of 1 corresponds to a log likelihood ratio value of 0. And at this point, it doesn't matter whether it was the same source pair or a different source pair. The two cross at that point, and they both give a penalty value of 1. So you're taking penalty values 1, 1, 1, 1. You take the mean of those, it's 1. So a system that provides no useful information will give you a CLR value 1. This is why our threshold is 1. If the system is giving you a CLR value less than 1, it is providing you with useful information. The lower the value, the more useful, but a value of less than 1 is giving you some useful information. And a well-calibrated system will have a CLR value that is less than or equal to 1. If you validate your system and your CLR value is greater than 1, that means your system is uncalibrated or is miscalibrated, and this can be fixed by appropriately calibrating the system. Just because the value is less than 1 does not necessarily mean that the system is well calibrated. For example, let's say you got a CLR value of 0.9. Maybe if you calibrate it, you might end up with a CLR value of 0.1, right? But calibration is something you should do anyway. You should do the calibration and then you validate. Here are some examples of different systems that are calibrated using the same calibration data. The data represented the conditions of an actual case. These are all different forensic voice comparison systems. The top two are older technology. In fact, this technology is about 20 years old, and they produced a CLR value of about 0.6. The middle set are newer technology, iVectors, and they produce lower CLR values going from about 0.45 to about 0.27. And then the bottom three are the newest generation of technology, which are giving us lower CLR values, 0.25, 0.21. So this allows us, because we've had a whole bunch of different systems all validated on the same test set, this allows us to do a baseline validation so we can see how well different systems perform relative to each other. I would suggest this is prior to, you do this prior to beginning your case. This is a very general validation. But based on this, I would obviously decide I'm going to use X vector systems. That's the system I'm going to use to do my case. I'm not going to choose one of the older technologies because the older technologies don't work as well. Now I'm actually working on my case. I need to do a case-specific validation. So these are results. They're somewhat modified, but they're based on an actual case that we've been working on this year. And this is a case, again, a forensic voice comparison case. What I'm showing you is different populations. One of these populations was relevant for the case, but I'm showing you two different populations. One involving female speakers, another involving male speakers. And we had, for the question speaker recordings, we had two different recording conditions. So these are different technical conditions which involve putting a compression that loses information, but they affect the conditions. And the other thing in this case, where there were multiple different question speaker recordings and that had different durations. So for the actual case, we took the exact durations of speech we got out of each question speaker recording, and we did a validation for that exact duration of speech. For the results I'm showing you here, we've done some fixed values. We've done 5 seconds, 10 seconds, etc. One of the things that's very obvious that you can see in this, this duration on the x-axis, as duration increases, the performance of the system improves. It's the same base system. It's actually different variants because for each set of conditions, including each duration, we have retrained the system, including doing a calibration under those conditions, right? So these are actually different systems or different system variants. But if we do that, we can see that as duration increases, the performance of the system improves, CLR gets better, and you can see that we've got an asymptote, for example, by 90 seconds, performance is leveled out. But for shorter durations, you can see you get poorer performance. And this is what I was talking about before. We have an interaction between the system and the conditions, right? So we would look at any one of these sets of conditions, the results for any one of these sets of conditions, and we'd say, is this system good enough to be used under these conditions in this case? Certainly, they all have CLR values much less than 1. So under those, we would be happy for us to use it. And we're actually quite impressed by the results we got out, even for very short duration recordings of 5 seconds. This is much better than the performance we would have gotten out of older technologies. Let's move on to tip plots. Tip plots are a graphical representation of results. How do we produce them? Again, we would start by putting in a whole bunch of same origin pairs, putting in a whole bunch of different origin pairs, and we get the likelihood ratios out of those. What we have here, let's focus on the same origin pairs, which are the blue curves rising to the right. We take all of our same origin log likelihood ratio values, and we rank them in order from smallest to largest, and then we can look at the cumulative proportion. So we're going from small to large on the x-axis, and we're looking at the cumulative proportion on the y-axis. So it's the cumulative proportion that would be less than or equal to the value on the x-axis. So if you look at the top panel and we look at a log likelihood ratio of 0, i.e. a likelihood ratio of 1, on the top panel, it looks like about 10% of the same source likelihood ratios had values less than 1, had log likelihood ratio values less than 0. Again, looking at the top panel, if we go to a likelihood ratio of 10, log likelihood ratio of 1, that looks like about 50% of the same source log likelihood ratios had values less than 1. Right, 50% had likelihood ratio values less than 10, which means about 50% had likelihood ratios greater than 10. And we could go up, let's look at this line here. This is 100, or a log 10 likelihood ratio of 2. And it looks like about 85% of the same source likelihood ratios had values less than 100. But that means that 15% had values greater than 100. And you can look down and you see the other panels. You can do the same for the different source. The different source pairs are plotted in reverse. It's values that, so it's cumulative proportion of values that are greater than or equal to the value on the x-axis. And the difference here was the different durations. This was 5-second long question speaker recordings. This was 20 seconds long. Here's 60 seconds. The corresponding CLR values were 0.45, 0.21, and 0.12. And this is also where we can, so the other thing you can see there is as the performance get better, these curves, they kind of scissor down. The blue curve, the same speaker curve, on average moves further to the right. The red curve, the different speaker curve, on average moves further to the left. Now we actually get our likelihood ratio from a comparison of our actual non-questioned recordings. And then we can see, using the tip plots, is that value we got actually supported by the validation results. For example, let's imagine we got a very good likelihood ratio value. Let's imagine we got 10,000 as our likelihood ratio. So that corresponds to a log 10 likelihood ratio of 4. If our recording, question speaker recording was 60 seconds long, well, it looks like actually in our test set, we did have a very small number, maybe about 1% of our same source comparisons that were greater than 10,000. So if we got a likelihood ratio of 10,000 from our actual question non-speaker recording, then yes, that would be supported by our validation results based on validating on 60-second long recordings. What, however, if instead of that being a 60-second long question speaker recording, it was only a 5-second long question speaker recording, and we got 10,000 as a likelihood ratio value. Well, that we have to look up here. Well, that's way beyond the highest likelihood ratio we got out of our test set. This one, it's certainly above 100. It's maybe 200-300 is where we're at, but that's a long way from 10,000. And so if we got a likelihood ratio of 10,000 from our actual comparison of our non-in-question recording in this case, and it was only a 5-second long question speaker recording, I would be very suspicious. I would say, no, that result is not supported by our validation results. I would suspect that something has gone wrong. Maybe the data we used for training and for validating our system did not actually represent the conditions of the case, or did not represent the population for the case. Something's gone wrong, and that value would not be supported by these validation results. Whereas, if in fact the question speaker recording was 60 seconds, I'd be happy. I would be very wary if it's 20 seconds. Obviously, if you're just a little bit above, that seems reasonable. If you're within the range you got from your validation results, it's certainly supported. But if you're way beyond it, then it would not be supported. Okay, last set, we only have 10 minutes left. I'll talk about some reflections on general issues. So validation is black box testing of the whole system. Validation requirements, in my opinion, should be exactly the same, irrespective of the internal architecture of the forensic comparison system. So it shouldn't matter whether you're dealing with a system based on relevant data, quantitative measurements, and statistical models, or whether you're dealing with a system based on human perception and subjective judgment. The validation requirement should be the same. I've said this already, I'm going to hammer it home. Calibration is an essential thing to do as part of evaluation. It's something you should do before you validate. It's not, you don't need to measure degree of calibration. What you need to do is actually calibrate and then validate. And once you have calibrated, I would argue that there is actually then no meaningful metric of degree of calibration. If you want to understand why, I would refer you to this recently published paper, or I'd be happy to have a conversation with anybody about this later. Another key point that I want to make is there is no one-size-fits-all validation. If you're doing anticipatory validation and a case comes in, you have to decide, are the conditions of that case, is the relevant population for that case sufficiently similar to the conditions of an existing validation report? If you're doing case-by-case validation, you need to say, can I get calibration and validation data that are sufficiently representative of the conditions and the relevant population for this case? There's no one size fits all. Validation should be fit for purpose. As Didier alluded to earlier, I'm hedging this and trying to word it carefully. I would suggest, at least as traditionally interpreted, it could be that validation based on ISO 17025 is not fit for the purpose of validating forensic comparison systems in the context of casework. I get the feeling that sometimes people are shoehorning things into a framework for validation based on ISO 17025. And then the results are not, maybe those results are not really what you need in the context of casework. And things that you do need in the context of casework may be missing. So some potential solutions, a short-term solution is think about potentially a different interpretation of ISO 17025. The long-term solution, again, as Didier was alluding to, is develop new ISO standards specific for validation of forensic comparison systems. That's not actually on the current schedule, but we're hoping to put it on a future schedule. I'd like to say something about consensus development. Good consensus development. You have researchers and practitioners that figure out what is fit for purpose practice. And there's then a consensus about what is fit for purpose practice. And since that consensus then exists, you then write guidelines and standards based on that consensus. So the fit for purpose comes first. There's an agreement about what's fit for purpose. There's a consensus about what's fit for purpose. And then you can write standards and guidelines explaining that to inform other people and to give yourself a checklist that you can then make sure that you're following all the things that we all agree are fit for purpose. Bad practice is we take existing practice, there's a consensus about existing practice, we therefore develop standards and guidelines describing existing practice, and then because there's a guideline or a standard, we say because there's a guideline or standard, whatever you're doing that follows the guideline or standard is fit for practice. It's fit for purpose, right? This is backward logic, right? First one good, second one bad. I've written about that, and my colleagues have written about that. There's a couple of references there. And I think that's the last thing I have to say. Oh no, one last thing. Okay, here's my dream for the future, right? That courts should require meaningful validation. Courts should inquire about whether the validation data were representative of the relevant population and reflective of the conditions of the case. Court should consider whether the validation results are good enough for the court's purpose. The court might decide, yeah, okay, CLLR of less than 1, it's 0.9, but you know, our likelihood ratios only come out to be something less than 10 or 1/10. That's not good enough. That's, you know, we're not going to spend the time on that. We want potentially to be able to get larger values in either direction. And the court should consider whether the likelihood ratio value for the comparison of the question source and non-source item is actually supported by the validation results. So that's my dream about what the future will be. So thank you very much.